All right, up next, lipids, saponifiable triacylglycerols. That is a hard word to say. All right, so let's talk about our triacylglycerols. Let's break this word down. All right, so what we have, tri. Well, we know tri. That's terrible. We know that tri means 3. The next is acyl. That's our functional group. So our acyl is going to be an ester, and our glycerol, all, ends in an OL. That is going to be an alcohol. So we have essentially our alcohol connecting to our, well, let's just continue on, shall we? All right, so we have simple triacylglycerols. These are going to be 3 identical fatty acid chains. So when I'm looking at this, and remember that with our esters, right, we are doing, well, these are created through esterification. So I have an alcohol that is going to be this component. Hold on. This component right here is what was my glycerol. And then I have my fatty acid, or my acid component, which I'm going to highlight here in orange. Okay. And so that fatty acid is going to give me a long chain, a long tail. So if I have a simple triacylglycerol, I'm going to have 3 identical fatty acid chains. It'll look all the same. And again, with these, I am still going to have a polar head. Now notice this time it's an ester, so I don't have that hydrogen bonding. I can still accept a hydrogen, still accept a hydrogen, but it's not going to hydrogen bond with itself. But it's still polar. And then these R groups are going to be nonpolar, my nonpolar tails. If I have 2 or 3 different fatty acid chains, this is called a mixed triacylglycerol. And as you can see here, this is what this indicates, is that I have 3 different chains, R prime, R double prime. Okay, so as I mentioned in the last slide, esterification this is the result of esterification. We're taking glycerol, or alcohol, and reacting that with 3 fatty acids to give us our triacylglycerol. It is a reaction that occurs under equilibrium, so it's very important that excess glycerol is used. That's going to push that reaction towards the products. Okay, so here is the practical application of this. So this is the difference between fats and oils. So fats, and that is indicated with, or that is shown here, this guy right here circled in purple, that is a fat. Fats tend to be solids at room temperature. Now the reason for this, all of my chains on that particular triacylglycerol they're all saturated, right? And so that means that these chains can actually stack on each other. Okay, so that's going to allow for more dispersion forces, right? So your tails, you have dispersion forces, and in your heads, you've got dipole-dipole interactions. Well, the more dispersion forces I have, the more, the stronger the interaction, so the more likely it is that this particular triacylglycerol will be a solid. This means also that the melting point will be higher. Now, again, we've noticed here that for this particular example, it's completely unsaturated. So the structure for fats is going to have none to very few double bonds. This is going to look different than our oils. So this particular structure has 3 different fatty acid chains. And notice that I've got, I have all of some cis in there, we've got a trans, but basically what I've got is I've got kinks in those chains from those double bonds. that's going to make it very difficult for those chains to stack. So it's going to reduce the number of dispersion forces. So this is going to make oils, liquids at room temperature, means they're going to have lower boiling points. There's less dispersion forces to interrupt. And these are going to have many double bonds.